So yeah, good evening. Today is the week 11 of the live interactive session of the course Introduction to Atmospheric and Space Sciences. We will begin today's session. Okay. So last class, if you guys remember, we were discussing uh, last class we were discussing how the plasma various types of various magnetic and electric fields. So initially we started with a uniform electron, which is basically static in nature, which means both dou E by with respect to space and with respect to time, the electric field that we considered was uniform. So we found that in the presence of a homogeneous static electric field, the particles within the plasma was found to be accelerating along the direction of the electric field. So that's what we saw in case of a homogeneous electric field. Whereas when we came to uniform magnetic field, homogeneous magnetic field, the particle was found to have a circular motion, have a simple circular motion. There is no additional component of velocity. So the velocity of the particle was considered to be zero. Velocity is not having an additional component of velocity. In that case, we found that in the presence of a homogeneous static magnetic field, the particle will execute a simple circular motion. Then we considered the case when there was a component of velocity which is parallel to the magnetic field to the particle. So the particle was found to move in a helical path. So it was moving in a helical path in the positive z direction. So these were the three things that we learned in the last class. So in case of a homogeneous static electric field, we found that the particle will be accelerated along the direction of the electric field. And second one, we found that in the presence of a homogeneous static magnetic field, the particle was found to execute a circular motion, given the particle is not having a velocity component. The third case, we considered again a homogeneous static magnetic field, but in this case, we considered that the particle is having a velocity component which is parallel to the magnetic field. And we found that the particle will move in a helical path. So these were the main things that we learned in the last class. So today we will be considering a magnetic field. And one more thing we learned was like when we combined both this uniform magnetic and electric field, then the charged particles experienced a drift velocity, and it was found to be moving away from the guiding center, and we call the drift velocity as E cross B. So in the presence of both electric and magnetic field, we found that the particle experienced a guiding center drift, which we called as the velocity E cross B. Now let's move on to in the presence of an inhomogeneous magnetic field, how the particles will be behaving. So that is what we are going to learn today. So we are considering a magnetic field which is inhomogeneous in terms of both space as well as in terms of time. So suppose the field is changing as the particle is moving. So if the particle is moving, suppose at x is equal to 0, the magnetic at y is equal to 0, the magnetic field that it experiences will not be the same at another point, maybe y is at another point in y. So as the particle is moving, the field is changing. So the magnitude of the field is changing in time as the particle is moving. So it basically means that at each and every point, as the particle moves, it is experiencing different magnitudes of the field. So we will introduce this inhomogeneity into the picture by including a term which is known as the length scale of inhomogeneity. So we will be introducing a term L, which is basically known as the length or scale of inhomogeneity. So what we are basically trying to do, we are trying to find how a particle behaves, plasma particle basically, in presence of a inhomogeneous magnetic field. So as a first step, we are introducing a length scale, which is a scale L, which is basically known as the length of inhomogeneity or scale of inhomogeneity. So what does it basically means that? So this is the distance. L is the distance. So what is L? L is basically the distance after which becomes inhomogeneous. After which magnetic becomes inhomogeneous. Suppose R is a distance. If R is than L, then the magnetic experiences B is homogeneous. Whereas the distance R is greater than L, the magnetic field that it experiences will be inhomogeneous. So this assumption we are taking for the problem, simplifying the problem. Yeah, for simplifying the problem. So basically, the field can be assumed to be homogeneous as long as the distance is less than L. And once we cross this limit capital L, the magnetic field will become inhomogeneous. So we can define the radius of gyration RL, which is basically the radius of the circle that the particle creates in the presence of a homogeneous magnetic field. You guys remember we learned it in the last class. So that is radius of gyration. So we can define that the radius of gyration, which is mv by qb. This also we learned in the last class. This equation mv by qb is very much less than L. So we have the radius of gyration is very much less than L. L. So the scale over which the magnetic field becomes inhomogeneous is much larger compared to the radius of gyration of a particle. It can be an electron or it can be whatever be the particle. So basically, to put the things simple, we are putting forward these assumptions. So we are considering that the radius of gyration of the particle is very much. So now let's consider a magnetic field. So I hope. So what we are basically doing is we are we are trying to find out how a particle will behave in the presence of a hinged magnetic field. Inhomogeneous in the sense the magnetic field is changing with respect to space as well as with respect to time. So the moving in the magnetic field with variance in different magnitudes at different points of time and space. So, in order to simplify the problem, we introduced a term which is basically known as the scale of homogeneity or length of inhomogeneity. Scale or length of inhomogeneity. So, as long as the distance is within um, this length of inhomogeneity, the magnetic field is considered to be homogeneous. And once we cross the scale of this length L, then it becomes in. Here we are considering the radius of gyration, which is RL, defined by mv by qb, is very much less than L. So the particle is not encountering the inhomogeneous magnetic field as it is moving in a circle. Okay, so that is the basic assumption that we make. So now consider this is X, this is Y, and this is Z. Now we are considering a magnetic field in the Z direction. So this is the direction of the magnet B, Z. And let us consider that the gradient of the magnetic field is in the Y direction. The gradient of the magnetic field is in the. Yeah, Ritika, you want to ask something? Your hand is up. Yeah, good evening. Yeah, good evening. Okay, yeah, please. Yeah, okay. Okay, can you tell me the values again? Hmm. 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 Okay. Hmm. Okay. 5.05 into 10 raised to minus 4 Tesla, right? 0.4. Okay, 0.45 into 10 raised to minus 4 Tesla. Okay. So the basic equation is RL is equal to MVQB. Okay. Here B is just 0.45 into 10 raised to minus 4 Tesla. So since it is an electron, E is known to us, which is basically 1.6 into 10 raised to minus 90. Okay. And here we have MV. Kinetic energy is given. So kinetic energy is half mv square. So m is also known to us since it is an electron. It is 9.11 into 10 raised to minus 31 kg. Right? So v is the only parameter which is missing here. So since kinetic energy is given by half mv square, we can write velocity is equal to 2 into kinetic energy by n, the whole root. So if you substitute this, RL will become m into root of 2 kinetic energy by m by q b. M and root m will be gone, and it will be root of 2 kinetic energy into m by q into b. Now I think we have all parameters. We know the values of all parameters, right? 2 into 10 into 10 raised to 6. Yeah. 1.6 into 10 raised to minus 19 into mass of the electron, which is given as 9.11 into 10 raised to minus 35 whole root divided by 1.6 into 10 raised to minus 90 into 0.45 into 10 raised to minus 4. Now you do the calculate the value and you get. Fine? So we'll continue. Okay. Yeah. So we are considering a magnetic field which is basically acting in the z direction, and the magnetic field is changing along the y direction. So the delta B is changing basically along the y direction. This is the direction of delta B. So what does it basically mean is that this is the magnetic field. This is along the z direction, and as we go up in the y direction, it is coming closer to each other. This means the magnetic field is becoming stronger. So here the magnetic strength of magnetic field is less, and as we are going up in the y direction, this is becoming more stronger. When it becomes closer, it is more stronger, and when it is becoming far apart, it is weaker. So as we move along the y direction, the magnetic field is becoming more strong. So this is a basic thing. We are considering a magnetic field which is basically acting in the z direction given by Bz, and we are considering that the gradient of the magnetic field is changing along the positive y direction. Okay, so these are the basic assumptions that we make. Now let us consider the gradient of the magnetic field. So if we write B, B will basically be a function of z. So x direction the value will be 0, y direction the value will be 0, and it will be Bz, and it will be changing along y. So B will basically be acting in the z direction, and the state is changing as a function of y. So this is the magnetic field that we are considering. So as we were discussing, basically as long as we are within the distance L, the magnetic field is homogeneous, but if you cross the length scale L, the magnetic field changes. So if you guys remember, in case of homogeneous magnetic field, we have seen that the particle experiences a force which is basically given as F is equal to Q into V cross V in a homogeneous magnetic field. So this was the equation that we learned. F is equal to Q into V cross V. So here when we do the cross product, so I, J, K. So V can be written as Vxi plus V by J plus Vz K. And V is basically Vz K. It only has a component along the Z axis. So it will be Vx, Vy, Vz and 0, 0, Vz. So if we take the cross product, then it will basically become F is equal to I into Vz Vy minus J cap along the so along the I direction it will be Vy into Vz minus Vz into 0, which is basically Vy into Vz itself, and along the J direction or Y direction it will be like this, cross product like this, it will be Vx into Vz, and again this component will be 0, and along the K direction both will be 0, Vx into 0 minus Vy into 0, both will be 0. So minus J into Vz Vx plus K into 0. So if we write it in component form, Fx will be, Q is also here, Q is also here. Fx will be Q Vz Vy I, and Fy will be minus Q Vz Vx. So this will be Fy and Fx and Fy, and Fz will be 0. So these are the three components of the force. So here Vx and Vy. So as we said, since the magnetic field is acting along the z direction, so Vx and Vy are perpendicular to the magnetic field. Vz and Vy are perpendicular to the magnetic field B, whereas Vz is parallel to the magnetic. So basically, it is not being altered by the magnetic field. The V set, which is a parallel component, is not being altered by the inhomogeneous magnetic field. There is no force acting along the parallel direction. That's what it basically means. So, equation was Fy or m dvy by dt was found to be minus q Vx Vzj and m dvx by dt or Fx was found to be q Vy Vz. So these are the two equations. So earlier in case of homogeneous magnetic field, we have solved these equations and we have got the solutions. And we found that the particle is executing a circular motion in case of a magnetic field. So in this case, since the magnetic field is varying, as I said, it is not same. It is varying along the y direction. So the particle will be, because of a homogeneous magnetic field, the particle will be having a circular motion with the radius of gyration r. So in case of a weaker magnetic field, or in case of here, the radius of gyration will be high. Whereas as the magnetic field becomes stronger, the radius of gyration becomes less. So as the particle is moving along the y direction, the radius of gyration of the particle changes. The radius of gyration of the particle RL changes as it moves along the y direction. So in case of a homogeneous magnetic field, we found that the particle is moving in a circle, having a circular motion with the radius of gyration RL given by md by q. Now in case of a inhomogeneous magnetic field, we found that as the particle is moving along the y direction of this inhomogeneous magnetic field, the radius of gyration is not constant, but it changes with respect to as it is moving along the y direction. So whenever the magnetic field is less, the radius of gyration was found to be high or large, and as the magnetic field is shrunken, the radius of gyration was found to be getting smaller and smaller. So this leads to the formation of a drift velocity. So the particle starts to drift from the center point. So the difference in radius of gyration in radius of gyration as it moves along the y direction creates drift velocity. So earlier we assumed that the length of inhomogeneity must be greater than RL of a single particle to make sure that the particle, while gyrating in one orbit, will not experience any inhomogeneous magnetic field. So here in case of So as I said, the particle is now having a drift velocity because of the changing magnetic field. So a few guys would have remembered the drift velocity is we have derived before in case of both electric and magnetic field. In the presence of an electric and magnetic field, the drift velocity was found to be like this. And in a more generalized form, it can be written as 1 by q into F cross B by V square. this is the additional force that the particle is experiencing in a magnetic field. So in this case, it was an electron, it was an electric field, and here in this case, it is basically the gradient of the magnetic field. So now, as the magnetic field is changing with respect to y, if we write the change in magnetic field, so B0 is the initial magnetic field, or it is the magnetic field at point y is equal to 0, then we can expand the equation. We can expand the equation in terms of Taylor series. So it will become B is equal to B0 R into del B0. Or since the changes in the B direction, we can write B is equal to B0 plus Y dou B by dou Y. Because dou B by dou X and dou B by dou Z are 0, and we can just expand it in the Y direction itself. So it will be B0 plus Y dou B by dou Y plus higher order terms will also be there. So we can neglect the higher order terms, and it will reduce to B is equal to B0 plus Y dou B by dou Y. So this is how the magnetic field is changing in the Y direction. So as I said, we have already derived the so we earlier we found that the force that is experienced by the particle in the x direction is basically Fx is equal to q vy vz into I, and Fy was found to be minus q vx vz into G. If you guys remember, we had found the solution for these differentials. So this is basically mdv x square md square vx by dt. Sorry, dvy by not d square, dvx by dt square and mdvy by. This is basically a differential equation. So we had found the solution for this differential equation in case of an homogeneous magnetic field, and we found that the solution for the equation in the last class we had found that the solution of the equation was H is equal to RL sin omega Ct, where omega is the critical frequency that we discussed earlier. So Bx is cos omega t, and y we found the solution as RL cos omega t, and Vy as V perpendicular sin. So we got the this is a solution that we got in case of a homogeneous magnetic field. Now if we substitute this equation in our current drift velocity. So drift velocity, we will substitute this in the force equation, Fx and Fy. So Fx is basically q vy vz, which becomes q vy into vz is, because it is changing, we have derived this equation b0 plus y dou b by dou y. So if we substitute q vy into b0 plus y dou b by dou y. This is Fx, and we know what is Vy, q into Vy, the solution is V perpendicular sin omega t into B0 plus y dou b by dou y. And sorry, again y also we can substitute. We know the value of y also. What is the solution for y? B0 plus y, we got it as RL cos omega t into dou b by dou y. So once you substitute the solution, it will become like this in case of an inhomogeneous magnetic field. And Fy is minus q Vx vz. It will become minus q Vx as V perpendicular omega t into b0 plus again x plus like this will again y dou b by dou y, dou y will be RL cos omega t dou b by dou t. This is fy and this is fx. Now and fz will be 0. Now we want to find the average value of the force that the particle will experience as at a distance of r at one radius, radius of dilation. What is the force that it experiences? So we will find the average of the force that it experiences along the circle. Basically, as it travels from 0 to 2 pi, what will be the force? So we will average the force in all the directions. Average of fx, average of fy, and average of fz. Average of fx will become, we will open the bracket as well, q b perpendicular into b0 average of sine omega t plus RL into average of sine omega t cos omega t dou b by dou y. So the average of sine omega t is basically 0 and average of sine omega t cos omega t is also 0. So average of fx, and we are considering the particle motion from 0 to 2 pi, will come to be 0. And we already know that the average of fz is also 0. Now the only term that is remaining is fy. So the average of fy will become minus q b perpendicular b0 cos omega t plus RL, this is average of cos square omega t into dou t by dou y. So average of fy will become, so average of cos omega t is 0 and average of square omega t is half. So substituting, average of fy will become q v perpendicular will become 0. This term will become 0. Cos square omega t is half into dou b by dou y, or average of fy can be written as minus q v perpendicular RL by 2 into dou b by dou y. So this is the force that is experienced by a particle in a magnetic field which is acting along the z direction and the gradient is along the y direction. The gradient is del. So the magnetic field is basically d z of y. In the presence of an inhomogeneous magnetic field, this is the force experienced by the particle. The force is basically acting. The force is along the y direction. So now what we want to find is the drift velocity of the particle. So drift velocity is given as 1 by q f cross b by b0. So here the force is the extra force that is acting is the inhomogeneous magnetic field. So when we substitute fy from this to the equation, the drift velocity will become ve will become 1 by q average of fy cross b by b. So it will be 1 by q into fy is minus q b perpendicular So this will be minus q v perpendicular RL by 2 into rho b by rho y, which is basically acting along the y direction j cross b z, which is acting along the k direction. So we have to take the cross product by b square. The cross product of j cross k is I. So this will become, so q and q will go. We are left with minus v perpendicular RL, and b square and p will be on here. So v perpendicular by RL by 2b rho b by rho. This will be acting in I direction, positive I direction. So this is the equation for this is the equation for the drift velocity. So what we were discussing the force that we were discussing behave in the presence of an inhomogeneous magnetic field. So we considered that the magnetic field is acting along the z direction and the gradient of the magnetic field, and we found the force experienced by the magnetic field, which is only acting in the y direction. That will be minus q v perpendicular RL by 2 into rho p by rho y, and because of the in the presence of an inhomogeneous magnetic field, the particle there will be a change in the radius of gyration of the particle. So due to the change in the radius of gyration of the particle as it moves along the y direction, it will basically lead to a drift velocity. So the magnitude of the drift velocity is given by minus v perpendicular RL by 2bz into rho b by rho y, which is basically acting along the I direction. So here what happens is that this is z, this is x, and this is the direction of the magnetic field. This is the direction of delta B, and now this became the direction of velocity. The particle will be moving in this direction, perpendicular to both. B is perpendicular to both B and delta. This I. So this is basically the gradient of the magnetic field. So this can be called as the gradient drift velocity. So V delta B. So as we can see from the equation, in case of so here if we substitute, here we don't see any term that Q, but when we substitute the value of RL, it is basically MV by QB. So as we know, Q is positive for ions and is negative for electrons. So in case of electrons, if Q is positive, Q is negative, VE will become positive. So I is also positive. So it will be in the positive I direction. The electrons will move in the positive I direction. Whereas when it is ions, so this term will be positive. So the negative sign will come. So negative I direction it will move. So due to the drift velocity, with the inhomogeneous magnetic field, there is drift velocity. So this is VE, direction of VE. And in case of electrons, it is along the positive X direction. And in case of ions, it is along the negative X direction. So in case of homogeneous magnetic field, we saw that the electrons and ions have gyrate in the opposite direction. So if you guys remember, we learned that in case of ions, the radius of gyration was in this direction, like this. In case of electrons, because of its smaller mass, the radius of gyration was in this direction. So the direction with the electrons and ions gyrate was different. in case of a homogeneous static magnetic field. But here, but there was no charge separation or anything that was happening in case of a homogeneous magnetic field. But when the magnetic field becomes non-uniform or inhomogeneous, what happening is that the drift velocity, this term known as the drift velocity, is coming into the picture. And as we can see, the electrons and ions are moving in opposite directions. This will basically lead to a charge separation. So in the presence of an inhomogeneous magnetic field, a charge separation is also occurring because of the difference in the direction of movement in case of because of the difference in the direction of movement in case of electrons and ions. The drift velocity is having a direction, the positive x direction, and in case of ions, the direction of drift velocity is in the negative x direction. So that's why since the electrons and ions directions, there is a charge separation that is happening here, which was not present in case of homogeneous magnetic field. So this is happening only in case of a inhomogeneous magnetic field. So the separation of the charges this is the direction of velocity. So as I said, in case of electrons will be moving in the positive x direction like this with a smaller radius of gyration. And in case of the ions, it will be moving in the positive x direction like this, with a comparatively higher radius of, this is electrons and this is ions. Okay. So in case of ions, it will be moving in the positive, in case of ions, it will be moving in the negative x direction, and in case of electrons, it will be moving in the positive x direction. So this separation of charges, this is basically known as planetary ring current. Separation of charges lead planetary ring. Yeah. Yeah. So that's it about the gradient drift velocity. Now, when we consider uh, basically like magnetic, according to Maxwell's equation, del dot T is equal to 0. So it basically means that magnetic monopoles does not exist. Sorry. Del dot B is equal to 0, which basically means that the magnetic monopoles does not exist and magnetic field always converge and diverge. So if you are considering a bar magnet, suppose this is north and this is south, it will always diverge from the north and converge in the south. So magnetic field always exists in dipoles, it never exists in monopoles. The magnetic field lines are never straight, it is always having this curved structure. So this basically means that the magnetic field the strength of the magnetic field is at its maximum at the poles and is minimum, and it varies as a function of r. As we go away from the pole, it varies as a function of r. So consider a dipole. So this basically means that the magnetic lines are always curved and are always associated with a gradient and curvature of the magnetic field. So now we understood that the magnetic field is not uniform. So as we have, this basically is higher in the poles and it varies and is minimum, and it varies with respect to r. So one thing we understood is that magnetic field, there is a gradient. There is a gradient in magnetic field that we have already taken into consideration the gradient in the magnetic field, and we have found the gradient, the drift velocity due to gradient drift velocity. And another thing now we understood is that the magnetic field lines are never straight, but it is always having a curved structure. So there is always a curvature of the magnetic field line. So we have already taken into consideration the gradient. Now we have to account for the curvature also. Since the magnetic field lines are not straight, suppose this is the magnetic field line, and this is the radius of curvature RC, and this is the path of the particle that we are considering. Just moving along this. So this direction is the parallel, and there is a force that is acting perpendicular to the acting along the radius of curvature, which is basically the centrifugal force. So, so we will be discussing curvature drift velocity. So the drift velocity of the particle, which is coming due to the curvature in the magnetic field lines. So we'll be discussing curvature drift velocity. So Vr is equal to 1 by Q. So this is basically the equation for drift velocity. General equation for drift velocity. F cross B by D square. Now here F is the centrifugal force. It is basically mv square by r, we know. So here m v parallel square by r, and it is acting along the direction of r, which is rc. So while substituting, we will get centrifugal force F is equal to mv parallel square by rc into rc. Substituting, we will get Vr, or the drift velocity due to the curvature Vr is given by 1 by Q into F is mv parallel square by rc into rc cap cross B by B square. So this is the equation for Vr. Now rc cap can be written as rc by magnitude of this basic vector. So Vr is equal to 1 by Q mv parallel square by rc square b square into rc cross. So this is the equation for the drift velocity due to the curvature of the magnetic field. So Vr is equal to 1 by q mv parallel square rc square b square into rc cross b. And earlier we learned that the drift velocity due to the gradient of the magnetic field was mv perpendicular square by 2q into b cross del b by b. Okay, this is just another form of writing the equation. So we got the equation to be v minus v perpendicular RL by 2b set dou b by dou r. If we substitute the corresponding gradients and the direction of the magnetic field, we will get the same. We substitute bz and dou b by this, we will get the same equation. It will reduce to the same equation that we got. It is just another form of writing the equation. It is basically the same. So this is the gradient drift velocity. This is the curvature drift velocity. So this is the gradient drift velocity and this is the curvature drift velocity. So when we are considering the particle which is in the presence of an inhomogeneous magnetic field, the total drift velocity of the particle is basically the sum of the drift velocity due to the gradient plus the drift velocity due to the curvature effect. So it will become 1 by q m v parallel square by rc square b square into rc cross b plus mv perpendicular square by 2q into b cross then b by. So this is the b total drift velocity due to both gradient in the magnetic field as well as the curvature in the magnetic. So if we just have a look at the different directions, so this is the curvature of the magnetic field, this is the radius of curvature RC, this is the direction of V parallel, and this will be the direction of V perpendicular. So I think like the equation have been simplified in the actual NPTEL class and cylindrical coordinates. I'm not going to repeat the same thing, so you can go through it. Okay. So now let's move on to the planetary ring currents. So as we earlier discussed, it is coming because of the charge separation that is happening in the presence of the charge separation that is happening in the inhomogeneous magnetic field. So we have already discussed the velocity that is already discussed the equation for the drift velocity that is coming due to the curvature and gradient. So this basically here we will just discuss the current density, change in the curvature driven current density and the gradient driven current density. So I'm just going to mention the equations. I'm not going into the derivation. So there is both curvature driven current density and gradient driven current density. So the curvature driven current density is given by JR is equal to NQ into PR of ions minus VR of electrons. This is the drift velocity due to curvature in case of ions and in case of electrons. N is basically the number of particles. So in case of plasma, number of ions and number of electrons will be. So that number is given by capital N. Q we know is basically the charge of the electron. Just 1 point that's into 10 raised to minus 9. So this is curvature driven current density. We also have gradient driven current density. Gradient driven current density, which is given as J delta is equal to NQV again the same velocity of ions minus velocity gradient drift velocity of electrons. Now we write this if we just expand the equation for V gradient and V parallel, we can write current density due to the N by BQ into the kinetic energy of ions plus kinetic energy of electrons into V cross delta V. And in case of the curvature it is 2N B square BC square B square into kinetic energy. So W is basically the kinetic energy which is given by half mv square into RC cross. So this is basically the due to density due to gradient and due to curvature. Okay. Now let's just look at the two phenomena, air glow and aurora. I will be just telling what are the between these two phenomena. Okay, so okay, I can change. We will start with aurora. So aurora sorry, give me. Aurora and air glow. We will just write it side by side. Yeah. So air glow is basically a global phenomenon. So air glow is basically a global phenomenon. which is seen at every point on the Earth. Whereas uh, aurora is basically a local phenomenon which can only be seen near the poles. Okay. Then airflow, sorry, air glow is basically due to the interaction interaction of uh, solar radiation with atmospheric constituents. Whereas aurora is found due to the interaction of highly energetic solar wind particles, highly energetic solar wind particles constituents of with the constituents of Earth's atmosphere in the presence of a magnetic field. And the intensity, air glow intensities are very low. It is basically 1 or 2 of the order of 100 Rayleigh kind of. Whereas in case of, oh sorry, here intensity is very high. In case of aurora, the intensity is very high. It is coming on the order of kilo Rayleigh. Whereas in case of air glow, the intensities are very low. It comes in the order of 100 Rayleigh. And in case of luminosity, air glow luminosity is kind of uniform, whereas the aurora luminosity is kind of structured. So in case of aurora, as I said, the main it is basically due to the interaction of interaction of highly energetic solar wind particles with the constants of the atmosphere. So the interaction occurs basically with oxygen and nitrogen. So what happens is that the oxygen and nitrogen interact with the solar wind, and it emit radiation. There will be change in the energy state of the electrons from 1s to 1d, 1d to, if these are the different shells of the atom. So in case of oxygen moving from 1s to 1d, it basically emits radiation at the range of 557 nanometer, which is basically the green line, day glow emission. Whereas in case of the second one, whereas oxygen is 1d to 3p, then the emission is with the wavelength of 630 nanometer, which is basically red dim. So these are the basic differences between airflow and aurora. I think it is clear. Now we will move on to some problems regarding the drift. Regarding the drift velocity. So the first problem is to calculate the drift velocity at y is equal to 3 into 10 raised to 6 meter. If magnetic field varies as A is equal to B by Y, where A is given as 2 into 10 raised to 4 Tesla per meter, and kinetic energy of a proton in the magnetic field is about 2 electron volt. So we basically want to calculate the velocity So we basically want to calculate the velocity, drift velocity, but they haven't mentioned us that the curvature drift velocity or it is a gradient drift velocity. But they have given the gradient of the magnetic field, which is given by B by Y. So let's assume they want us to calculate the gradient drift velocity, which is B delta. So we are going to calculate the gradient drift velocity. So they have given the value of y, which is 3 into 10 raised to 6 meter. They have given A is equal to B by Y, and A is having a value of 2 into 10 raised to 4 Tesla per meter. So A is varying with respect to Y. And they have also given the kinetic energy is 2 electron, and we have, and it is basically a proton. Kinetic energy of a proton they have given. So what is the equation for the gradient of velocity? V delta V is given by mv perpendicular square by 2 qv square into rho v by rho y, which will basically be half mv square. This term can be written as kinetic energy. Kinetic energy by qb square into rho v by rho y. So the value of kinetic energy is given, which is 2 into 1.6 into 10 raised to minus 9, 2 electron volt. Q we know since it is a proton. V, V also they have given the value. Okay, just there is a mistake in the question. So this is B is equal to A by Y. Sorry. B is equal to A by Y. So B we can calculate from A by Y, and dou B by dou Y also we can calculate. So from here B is A by Y, which is 2 into 10 raised to 4 by 3 into 10 raised to 6, which will be this is the value of it will basically be 6.6 into 10 raised to minus 3. So this is the equation of B, which will have a unit of Tesla. Now we want to find, I'll write it here. Okay, so yeah, so B is equal to A by Y. We found it to be 6.66 into 10 raised to minus 3 Tesla. Now we want to find dou B by dou Y, which by differentiating this we will get, it will be minus A by Y square, which is equal to minus 2 into 10 raised to 4 divided by Y is 3 into 10 raised to 6 the whole square, which will be, please do calculate. Can you tell me how much you got? It is coming out to be 10 raised to minus 2 into 10 raised to minus 9. It was also negative, was also there. I hope I'm not doing mistake. No. Now we want to find the gradient of V, which is again which is kinetic energy by QB square into dou B by dou Y. The value of kinetic energy is given as 2 electron volt, which is 2 into 1.6 into 10 raised to minus 19 by 1.6 into 10 raised to minus 9. This is the charge of the proton into B square, which is 6.66 into 10 raised to minus 3 the whole square into 2 into B. B is having a value of into dou B by dou Y. Dou B by dou Y is having a value of minus 2.22 into 10 raised to minus 9. So 1.6 into 10 raised to minus 19 here and here will be 1. Then after calculating It is coming out to be minus 1 into 10 raised to minus 4 meter per second. Into 10 raised to minus 4 meter per second. 10 raised to minus 4 meter per second. So this is the answer. I think the negative sign is coming because it is moving in the negative y direction. So this is the gradient, this is the drift velocity due to the gradient of the magnetic field. I hope the things are clear. In the question, the things that are given is, they have given the value of y, which is 3 into 10 raised to 6 meter. They have given how the magnetic field is varying. B is given as A by y. They have also given the value of A, which is 2 into 10 raised to 4 Tesla per meter. Per meter, this much change is happening to the magnetic field. And they have also given the value of the kinetic energy of the proton, which is 2 electron volt. So from the basic equation, we substituted for so this was a basic equation, which is mv perpendicular square 2qb square into dou b by dou y. Here this term, which is basically half mv square, is the kinetic energy of the proton, kinetic energy of the particle. So half mv square, mv perpendicular square by 2 can be written as kinetic energy. So it will become into dou b by dou y. So b they have already given. They haven't given directly b, but they have given that b is a by y. They have given the value of a as well as the value of y. And by differentiating a by y, we can calculate the value of dou b by dou y. That also we did. And finally, we got the value of the velocity, drift velocity due to the gradient of the magnetic field. Now the next question. So the next question is to find the kinetic energy of a proton in the direction of the magnetic field. 3 electron volt. The curvature radius is 4 into 10 raised to 6 meter, which is perpendicular to B is equal to 1 Tesla. Find the curvature drift. Here we want to calculate the VR or the drift velocity due to the curvature of the magnetic field. So the things they have given as kinetic energy is 3 electron volt, which is 3 into 1.6 into 10 raised to minus 9. So kinetic energy they have given, and the radius of curvature also is given, which is 4 into 10 raised to 6 meter. They have also given the value of magnetic field, which is 1 Tesla. So again here the equation is 2 mv parallel square by q. Basically mv parallel square by q into rc into b. So they have given that the magnetic field is perpendicular to the curvature radius. So sin 90 will come. RC into sin 90 by RC square BC square. RC square B square. So this is B. So RC and B is perpendicular they have given. So RC cross B will become RCB into sin 90. And then everything else is the same. So now here we can multiply 2 on both numerator and denominator. So this will become, so this term will become again kinetic energy. So 2 kinetic energy by Q into RCB by RC square. So here what we did is, the basic equation is NV parallel square by Q into RC cross B by RC square B square. So here one thing they have given us the radius of curvature and magnetic field are perpendicular to each other. So RC cross B will become RCB sin 90, and then we are multiplying and dividing with 2 in both numerator and denominator, 2 into, and then it will become this NV parallel square by 2, this term will become kinetic energy and this 2 will remain. So it will be 2 kinetic energy by Q into RC by B by RC square B square. So this this will go, this will go. So finally, the drift velocity due to the curvature effect will reduce to 2 kinetic energy by Q into RC, Q RC. Now we have the values for all terms. So this will become 2 into kinetic energy is 3 electron volt, 2 into 1.6 into 10 raised to by Q was 1.6 into 10 raised to minus 19 since it's in case of a proton into RC as the radius of curvature, which is given as 4 into 10 raised to 6 into magnetic field is given as 1%. So this will become 2 into 3 into 1.6 into 10 raised to minus 19 here and here will be gone. So it will become 6 by 4 into 10 raised to 6, which is basically 1.5 into 10 raised to minus 6 meter per second. So this is the value of curvature drift, the drift velocity due to the curvature of the magnet. Okay, I hope this is also clear. Now let's move on to another problem. So the problem of the magnetic field and moment of a particle is 0.5 Tesla and 8 into 10 raised to minus 19 joule per Tesla. What will be the angle between the velocity and magnetic field if its kinetic energy is 2.5 electron volt and 2.5 mega electron volt? So this question is coming from the topic of that magnetic mirroring. So if you guys remember, this has been already taught in the NPTEL class. The equation that we require is the equation that we require is magnetic moment by kinetic energy is equal to sine square theta into B. So they have given us the magnetic field. So mu is the magnetic moment, B is the magnetic field, sine square theta by mu by kinetic energy is equal to sine square theta by B. So this is the V horizontal. This angle is basically theta. This is V perpendicular. This is the actual direction. So basically, after finding that the magnetic moment is conserved, I'll just so the basic idea was that the magnetic field has the ability to keep the magnetic moment conserved. So after finding that the magnetic moment is conserved in case of a magnetic field, the magnetic moment is basically given by mv perpendicular square by b. So we proved that. So in the NPTEL class, you would have proved that the magnetic moment is actually conserved within a magnetic field. So from that assumption, or this is theta, this is the horizontal, this is the direction of B. So So from here we can write, and this is the direction of B perpendicular. From this equation we can write B perpendicular is equal to B sine theta. You substitute, it will become M into B square sine square theta by 2B. So here this term is kinetic energy. So mu will become kinetic energy sine square theta by B, or mu by kinetic energy is equal to sine square theta by B. This is equation that we derived after finding that the magnetic moment is conserved. And sine, this is set 0 and this is dm max. At z is equal to 0, the magnetic field was found to be minimum, and as we are going, the magnetic field was found to be increasing. So sine square theta m by dm is equal to sine square theta 0 by b 0. We find the ratio, and the mirror ratio is given as dm by b0, or sine square theta 0 is equal to b0 by bm. Sine square theta is equal to b0 by bm. So the particle will be trapped within the magnetic field when theta m is equal to theta 0. Whenever theta is greater than or equal to 90 degree, then reflection or trapping occurs. And when theta is less than 90 degree, particle is lost. And that theta critical is given by sine inverse root of b0 by bm. When sine square theta 0 greater than or equal to b0 by bm, there is reflection, and when it is less than b0 by bm, it is lost. So these are the basic conditions for the particle to be trapped within the magnetic field. So this all comes from the conclusion that the magnetic moment is conserved within the magnetic field. So yeah. So here the magnetic field and moment of the particle is given. Magnetic field is given by 0.5 Tesla, and magnetic moment mu is given by 8 into 10 raised to minus 19 joules per Tesla. What will be the angle? We have to find theta between velocity and magnetic field, between B and B. If the kinetic energy 2 are there, if it is 2 electron volt and 2.5 mega electron volt. Now let's try the first case. When kinetic energy is 2.5 electron volt. And the kinetic energy is 2.5 electron volt. And the kinetic energy is 2.5 electron volt. We want to find theta, right? It is mu into B by kinetic energy is sine square theta. So this will basically be sine inverse. Or sine theta is equal to root of mu v by kinetic energy, which is 8 into 10 raised to minus 19 into 0.5 by 2.5 into 1.6 into 10 raised to minus 9, the root of the whole thing. It will come out to be it will give an answer of 1. So basically theta will be sine inverse of 1, which is 90. This is the value of theta in first case. Now let's consider the, just a second, I will just add one more slide. So yeah, in the first case when kinetic energy is 2.5 electron volt, theta is 90. Now the second case when kinetic energy is 2.5 mega electron volt, which is 2.5 into 10 raised to 6 into 1.6 into 10 raised to minus 19. So in that case, sine theta will become root of mu, again 8 into 10 raised to minus 19 into V, which is 0.5 Tesla, by kinetic energy, which is changing, which is 2.5 into 10 raised to 6 into 1.6 into 10 raised to minus 19. This will give you a value of will come around 10 raised to minus 3. So theta is sine inverse of 10 raised to minus 3, which is very small. Theta is very small, which means it is almost parallel to the theta is very, the vector V is almost horizontal. That's what it basically means, because theta is very small. So that was the second case. Now let's move on to the next question. So the question is, calculate the magnetic moment of a particle and the magnetic field of 0.8 Tesla and kinetic energy of 3 electron, and which angle is 30 degrees. So we want to find mu, basically it is the magnetic moment. B is given as 0.8 Tesla. Kinetic energy is given as 3 into 1.6 into 10 raised to minus 19 joule. Which angle theta is given as 30 degrees. So mu is basically sine square theta into kinetic energy by V. So mu by Ke is equal to yeah. This is the equation. Mu is equal to sine square theta into kinetic energy by V. So here everything is given. Sine square into theta is 30 into kinetic energy is 3 into 1.6 into 10 raised to minus 19 divided by B, which is given as 0.8. So it will give you a value of it will give you a value of around 1.5 into 10 raised to minus 19 joule per. So this is the value of the magnetic moment. So now this is the final problem. Find the Lamar's radius of an alpha particle of the kinetic energy is 12 electron volt and magnetic field of 0.4 Tesla. Lamar's radius is basically the radius of dilation, which is RL. It is an alpha particle. Kinetic energy is given as 2 electron volt. Magnetic field is given as 0.4 Tesla. So we want to find RL basically. RL is equal to mv by qb. And kinetic energy is half mv. From this we can find v as 2 kinetic energy by m. Root of 2 kinetic energy by m is basically velocity. So if we substitute velocity in the equation for radius of dilation, we will get m into root of kinetic energy by m by q, which is root of 2 kinetic energy into m by q. Now if we substitute, it will be 2 into kinetic energy is given as 12 into 1.6 into 10 raised to minus 19 into the mass of an alpha particle is basically 6.64 10 raised to minus 27 kg. So if we substitute this will be 6.64 into 10 raised to minus 27 divided by Q is 1.6 into 10 raised to minus 19 into B. B is 0.4. So this will be there is a root here. Root of 2 into root of 2 into 12 into 1.6 into 10 raised to minus 19 into 6.64 into 10 raised to minus 27 divided by 1.6 into 10 raised to minus 19 into 0.4. Can you tell me how much you are getting? I think I made some mistake. The answer is supposed to be 24.94 into 10 raised to minus 4. Sorry, it will be 0.125 centimeter. This is the value of radius of dilation. Did anyone got the answer? 2 into 12 into 1.6 into 10 raised to minus 19 into 6.64 into 10 raised to 27 divided by 1.6 into 10 raised to minus 19 into 0.4 into, yeah, it is coming to be, here one more 2 is there because the electron, the charge of an alpha particle is 2 into 1.6 into 10 raised to minus 9. Yeah, so this is coming out to be 1.24 into, it will be 0.125 centimeter. Please check the values. I think this is correct. Okay, so yeah, that's it about today. So today we were mostly discussing about how a particle will behave in the presence of inhomogeneous magnetic field, and we found that because of the magnetic gradient in the magnetic field, there will be a because of the inhomogeneous magnetic field, there will be a drift velocity, and we derived the equation for both in case of both the drift velocity because of the gradient in the magnetic field and also the drift velocity due to the curvature in the magnetic field lines. And we also learned that in the presence of an inhomogeneous magnetic field, there is a charge separation that is happening within the plasma, which was absent in case of homogeneous magnetic field. We also discussed about planetary ring currents and the current density. Just like the drift velocity has two components due to curvature and gradient, this also has two components. So one was curvature driven current density and another was gradient driven current density. We also discussed the equations regarding that. Then we discussed about two phenomena, air glow and aurora, and we came to know like air glow is basically a global phenomena, whereas aurora is local phenomena and is seen mostly in the poles. And this is air glow is mostly formed due to the interaction of solar radiation with the atmospheric constituents, whereas aurora forms due to the interaction of highly energetic solar event particles with the constituent of atmosphere in the presence of a magnetic field. And the intensity of aurora is very high, whereas the intensity of air glow is less comparatively. It's high. In case of air flow, it was found to be less. And aurora basically interacts with the oxygen and nitrogen atoms in the atmosphere, and the change in that the electrons move from one shell to another, and then during the process it emits energy and different wavelength. So we discussed the change from S to D as well as D to B. Then we also discussed about magnetic mirroring. So this is basically coming from the concept that the magnetic moment magnetic field within a magnetic field. So the particle will be trapped within the so we derived the equation for that and the conditions for trap. Then we did some problems. I think that's it